problem where we're trying to show that the product of 8 consecutive integers, and I'll show you why, but we want to show that the product of 8 consecutive integers can be written is a squared minus 1 times b squared minus 1, where a and b are, of course, integers. Now, this is a standard trick here. You have to add 1 right here. See, 40 minus 33 plus 1 gives you 8. Now, an easy way to see this is just think of this as from 33 to 34. You know there's going to be, that'll mean 33 times 34, so there's 2. So that's why you have to add this 1 here. So there's 8, which falls right into the lap of this nice lemma that says the product of 4 consecutive integers is equal to something squared minus 1. Now, this lemma is kind of everybody's favorite problem at the various math websites. This a version of this problem has been worked probably at 200 different math websites. But the reason why it's true is based on this interesting regrouping. What you can do is multiply n times n plus 2. It's just a rearrangement right here. So what you would get, or no, sorry, let's do n times n plus 3, and that would give us what? N squared plus 3n. And again, y'all, what I did here, and it's not particularly easy to see why this works, at least it wasn't for me, but n times n plus 3 is this right here. Okay, and then so we'll take the product of n plus 1 times n plus 2, and that'll give us n squared plus 3n plus 2, right? And this is basically the proof of this. I mean, it's a super famous, everybody does it. I think it even appears in the SMO junior section. But notice that this is in the form a minus b times a plus b. Let's see if I get that written in there. Okay, this is in the form a minus b times a plus b. And over here, this would be a squared minus b squared. Now, of course, we're taking a to be n squared plus 3n plus 1. That's what makes it work out. So it's kind of cool how that works out. And of course, 1 can be thought of as 1 squared up here, right? So you see, that's pretty slick. And so that's why this lemma is true. Just a very quick and dirty proof of why that's true. So why is that important? Well, we have 4 consecutive integers happening twice here because you have 8, the product of 8 consecutive integers beginning at 33. So let's see, here we go. We got this written down. We start at 33, we end up at 40. And you can see we just we apply the lemma to this block, 33 times 34 times 35 times 36, and you can see what happened here. This would be what, 3 times 33? That's exactly this part of it right here. Then over here, this would be 3 times 37, isn't it? 3 times 37 is 111. Okay, and that would be for this second block. So you see, we literally applied this lemma twice, and we end up with this expression right here, which is going to be in the appropriate form. Now, I just went ahead, I didn't do all the arithmetic, but I'll just write down the result. When you do the arithmetic, and I double checked all this, you'll get 1189, I believe right here, folks, 1189, right here, 1189 squared minus 1. Okay, and then right here you'll get, what is it, 1480 something? I don't know if I got this right or not. But anyway, it's here. I may have made a mistake on the arithmetic. But anyway, 1481 squared is what I'm getting right here, minus 1. Okay? And so that would answer our question about A and B, this would A would be equal to 1189. And B is 14. If that's not a mistake right there, but anyway, you can do it. You can verify. I think I got it right. 1481. That's what makes it happen, folks. So again, I thought it was kind of fun because you saw this problem when you first see this result. This is, it gets, I mean, literally at least I bet you 200 different websites did this particular problem, that the product of four consecutive integers is equal to n squared plus 3n plus 1 minus 1. A quantity squared. That's a result in put the 1 on this side is perhaps a little more natural, But I think a more natural statement of this is you take any four consecutive integers, take their product, and then add 1, and you're guaranteed to get a perfect square. So that we use that result to solve this particular problem. Okay, guess that does it.